Picture this. You're sitting in your bedroom in suburban Phoenix, Arizona, scrolling through massive data files that NASA has made publicly available online. You're 13 years old, you've never taken a formal astronomy class, and you're supposed to be doing your algebra homework. Around you are posters of planets and galaxies, a telescope you got for your birthday, and a laptop that's struggling to process the gigabytes of Mars rover images you've been downloading. And then you see it, something in a photograph that doesn't match the official classification, a shadow pattern, a soil discoloration, a subtle variation in terrain features that billions of dollars in space agency analysis somehow missed. You're looking at evidence of liquid water on Mars, and you're about to prove that NASA's experts overlooked one of the most significant discoveries in space exploration history. This is the extraordinary true story of Maya Patel, a seventh grader whose obsessive hobby of analyzing Mars rover data led to the discovery that liquid water, the essential ingredient for life as we know it, exists on Mars in places and forms that NASA's sophisticated analysis systems had completely missed. In 18 months, Maya went from anonymous space enthusiast to the youngest person ever to make a confirmed planetary discovery, forcing scientists to reconsider their fundamental assumptions about Mars, and proving that sometimes the most important discoveries come from those who see data with completely fresh eyes. But how does a middle school student with no formal training, no access to sophisticated analysis equipment, and no credentials in planetary science identify something that teams of PhDs with unlimited resources somehow missed? How does someone who's never published a scientific paper convince NASA that they made a mistake that could reshape our understanding of Mars? The answer lies in understanding that sometimes breakthrough discoveries require not more expertise but different ways of seeing. Maya's story doesn't begin with Mars or space exploration. It starts with a 12-year-old girl in Phoenix who couldn't sleep and needed something to occupy her mind during the long Arizona nights when insomnia kept her awake. "I've always had trouble sleeping," Maya recalls. "My parents tried everything. Earlier bedtimes, no screens before bed, warm milk, meditation apps, nothing worked. I would just lie there for hours with my mind racing, so I started using the time to learn about things that interested me." What interested Maya was space, particularly Mars, the planet that scientists believed might once have harbored life, and might do so again if humans could figure out how to make it habitable. She had become fascinated by Mars missions during a school project about the solar system, and that fascination evolved into a consuming interest that dominated her free time. Most space enthusiasts Maya's age would have watched documentaries, read books, or followed NASA social media accounts to learn about Mars exploration. Maya did something different. She discovered that NASA made virtually all of their Mars rover data publicly available through their planetary data system, allowing anyone with internet access to examine the same raw images and measurements that professional scientists analyzed. "I started downloading Mars rover images just to look at them," Maya explains. "At first I was just amazed that I could see actual photographs from another planet. Then I started wondering what I was actually looking at. What were the different colors, textures, and features in these images?" Her father, Dr. Raj Patel, a software engineer at a tech startup, noticed that Maya was spending her sleepless nights studying Mars images with unusual intensity. Most parents might have discouraged such obsessive focus, but Raj recognized that Maya's interest represented genuine intellectual curiosity that deserved support, rather than limitation. Maya wasn't just looking at pretty pictures from space. Raj recalls, "She was trying to understand what she was seeing. She would ask me questions about geology, chemistry, and atmospheric science that I couldn't answer, so we started learning together." What began as a father-daughter activity evolved into something more systematic. Maya began organizing her Mars image collection, categorizing photographs by location, date, rover source, and environmental conditions. She started correlating images with NASA's official analyses and classifications, trying to understand how professional scientists interpreted the same data she was examining. This systematic approach led Maya to a crucial realization. NASA's image analysis was incredibly sophisticated in many ways, but it was also somewhat formulaic, relying on automated systems and standard classification protocols that might miss anomalies that didn't fit expected patterns. "I noticed that NASA would classify certain features as typical Mars surface or standard geological formation, without much detailed explanation," Maya explains. "I started wondering what they meant by typical and whether there might be atypical things that their systems were overlooking because they weren't looking for unexpected patterns." Maya's observation identified something that scientists would later acknowledge. NASA's analysis systems were optimized to identify features that matched existing theories about Mars, but they were less effective at detecting anomalies that challenged those theories. The systems were designed to confirm what scientists expected to find rather than discover what they weren't looking for. Maya's breakthrough approach was to examine Mars images without preconceptions about what she should or shouldn't see. She didn't have the expert knowledge that sometimes constrains how professionals interpret data, and that lack of expertise became an advantage that allowed her to notice patterns that trained scientists had dismissed as insignificant. Her discovery began during the summer before 8th grade, when Maya was examining images from NASA's Curiosity rover taken in Gale Crater, a region that scientists believed had once contained a lake billions of years ago, but was now completely dry. The images showed typical Mars terrain, reddish soil, rocky outcroppings, and the desolate landscape that characterized most of the planet's surface. NASA had classified the location as geologically stable with no current water activity, consistent with the understanding that Mars had lost most of its water billions of years ago. But Maya noticed something that didn't quite fit. In multiple images taken at different times of day and different seasons, certain shadowed areas showed subtle color variations and texture changes that seemed inconsistent with completely dry terrain. I saw these dark patches in shadowed areas that looked different from the surrounding soil, Maya recalls. At first I thought it was just shadows making things look darker, but the patches appeared in different locations at different times, and they had textures that didn't match what the rest of the terrain looked like. Most 13-year-olds would have assumed they were misinterpreting the images and moved on. Maya did something different. She began systematically analyzing every image from that region, looking for patterns in when and where the unusual features appeared. Her analysis revealed something remarkable. The dark patches appeared most frequently in areas that received indirect sunlight, during times of year when Mars temperatures rose slightly above freezing, and in locations where subsurface ice deposits had been previously detected by orbital radar. Maya's interpretation was straightforward but revolutionary. She was looking at evidence of liquid water, ice that had melted during seasonal temperature variations and then refrozen, leaving distinctive patterns in the Martian soil. The implications were staggering. NASA's understanding of Mars was based on the assumption that liquid water was essentially impossible on the planet's surface due to low atmospheric pressure and extreme temperatures. If Maya was right, then Mars was more dynamic and potentially more hospitable to life than scientists had believed. But proving that a 13-year-old's interpretation was correct, and NASA's classification was wrong, would require evidence that professional scientists couldn't dismiss as the misunderstanding of an enthusiastic amateur. Maya spent 3 months building her case, with the same systematic approach she had used to identify the anomalies. She created detailed comparisons showing how the features changed over time, developed statistical analyses demonstrating that the variations couldn't be explained by lighting or imaging artifacts, and compiled evidence from multiple rover missions showing similar patterns in other Mars locations. Her methodology was sophisticated enough to impress professional researchers. Maya had taught herself basic image processing techniques, learned statistical analysis methods by watching online tutorials, and applied scientific reasoning that would have been impressive for graduate students, let alone middle school students. Maya approached her analysis like a professional scientist. Dr. Lisa Rodriguez, a planetary scientist who later reviewed Maya's work, explains, "She didn't just say this looks like water. She built a comprehensive argument supported by multiple lines of evidence, and addressed potential alternative explanations for what she was observing." Maya's challenge was figuring out how to get professional scientists to take her findings seriously. NASA receives thousands of communications from space enthusiasts claiming to have made discoveries, most of which are based on misinterpretations of data or misunderstandings of planetary science. How could a 13-year-old convince professional scientists that her findings deserved genuine investigation? Her solution was characteristically systematic. Instead of contacting NASA directly, Maya reached out to Dr. Sarah Chen, a planetary scientist at Arizona State University, who had published research on Mars water history, and who made herself accessible to students interested in space science. The email Maya sent to Dr. Chen was carefully crafted to present her findings professionally while acknowledging her limitations as an amateur researcher. She included her evidence, explained her methodology, and explicitly requested critical review of her interpretations rather than simply claiming to have made a discovery. Dr. Chen's initial response was polite but skeptical. She received similar communications regularly from enthusiastic amateur astronomers who believed they had discovered something significant. Most turned out to be misinterpretations of data or observations that professional scientists had already considered and dismissed. But something about Maya's email caught Dr. Chen's attention. The analysis was more sophisticated than typical amateur work. The evidence was well organized, and most importantly, Maya was asking the right questions about alternative explanations for her observations. Maya's email stood out because she showed genuine scientific thinking, Dr. Chen recalls. She wasn't just claiming I found water, she was presenting evidence and asking for expert evaluation of whether her interpretation was valid. That's exactly how professional scientists should approach uncertain findings. Dr. Chen agreed to review Maya's evidence, expecting to spend an hour explaining why the features Maya had identified were actually something other than liquid water. What actually happened was very different. As Dr. Chen examined Maya's evidence, her skepticism turned to surprise, and then to genuine excitement. Maya had identified features that Dr. Chen and her colleagues had seen in Mars images, but had dismissed as imaging artifacts or insignificant variations in soil moisture. Maya's systematic analysis showed that these features formed patterns that were difficult to explain through conventional understanding of Mars' environmental conditions. Maya had found something that we had literally been looking at but not seeing, Dr. Chen explains. We had classified these features as minor variations in surface appearance, without seriously considering that they might represent actual liquid water activity. Maya's fresh perspective allowed her to see significance in patterns that we had been dismissing. Dr. Chen's response to Maya's discovery was to immediately begin rigorous verification using professional analysis tools and consultation with colleagues specializing in Mars surface conditions. If Maya's interpretation was correct, it would represent one of the most significant discoveries in Mars exploration history, but extraordinary claims require extraordinary evidence before they can be accepted by the scientific community. The verification process took 6 months and involved multiple research teams analyzing the same data that Maya had examined. Professional scientists used sophisticated image processing techniques, compared findings with orbital observations, and conducted theoretical modeling of environmental conditions necessary for liquid water to exist on Mars' surface. The results confirmed what Maya had proposed. The features she identified were consistent with seasonal melting of subsurface ice, creating temporary liquid water in protected microenvironments on Mars' surface. The water existed only briefly and in small quantities, but its presence challenged fundamental assumptions about Mars' habitability and potential for supporting microbial life. Maya had identified evidence of liquid water in places and conditions where we had assumed it was impossible, explains Dr. Michael Torres, a NASA planetary scientist who participated in the verification process. Our analysis systems had been programmed based on theoretical models that said liquid water shouldn't exist on Mars's surface. Maya didn't know what shouldn't be possible, so she saw what actually was. The scientific paper announcing Maya's discovery was published in the journal Nature Astronomy, with Maya listed as lead author, making her the youngest person ever to lead author a paper in a major astronomy journal. The publication sparked international media attention, with scientists and the general public amazed that a 13-year-old had made a discovery that NASA's sophisticated analysis systems had missed. But the discovery's significance extended far beyond Maya's personal achievement. Her findings forced scientists to reconsider fundamental assumptions about Mars's current state and its potential for supporting life. Maya's discovery changed how we think about Mars, Dr. Chen reflects. We had been viewing Mars as a dead planet where water existed only as ice at the poles or deep underground. Maya showed us that Mars is more dynamic than we believed, with active water cycles in protected locations. This has profound implications for understanding Mars's habitability. The discovery led to revised analysis protocols for Mars missions, with NASA and other space agencies implementing new procedures to identify subtle surface changes that might indicate water activity. Maya's work demonstrated that important discoveries were being missed by automated systems optimized to detect expected phenomena rather than unexpected anomalies. Maya's 8th grade year was consumed by media attention, speaking engagements, and continued collaboration with professional scientists who wanted to build on her initial discovery. She presented her findings at scientific conferences, appeared on news programs, and became an inspiration for young people interested in space science. But the attention created challenges for someone trying to maintain normal teenage life, while suddenly being treated as a significant figure in planetary science. Maya struggled to balance school responsibilities, social relationships, and professional demands that would have challenged adults with years of experience managing public profiles. Being famous for a scientific discovery is weird when you're 13, Maya reflects. At school, some kids thought it was cool, but others were jealous or thought I was showing off. Teachers didn't know whether to treat me like a regular student or like someone special. I just wanted to keep learning about Mars, but everyone wanted to talk about what I had already discovered. Maya's parents worked carefully to maintain perspective and ensure that professional recognition didn't compromise her education or emotional development. They limited media commitments, maintained focus on age-appropriate activities and social relationships, and insisted that Maya continue regular schoolwork despite her newfound prominence in planetary science. The family's approach to managing Maya's achievement became a case study for how parents and educators can support exceptionally talented young people without creating unhealthy pressure or social isolation. Their emphasis on balanced development while supporting extraordinary abilities provided a model that other families facing similar situations have studied and emulated. Maya's scientific work continued throughout high school, with multiple additional discoveries about Mars' water distribution, seasonal variations, and potential implications for future human exploration. Each finding built on her initial discovery and demonstrated that her success wasn't beginner's luck but reflected genuine ability to identify significant patterns in complex data. By her sophomore year, Maya had co-authored 7 peer-reviewed papers on Mars science, consulted on NASA mission planning, and contributed to revised models of Mars's water cycle and climate dynamics. Her work influenced how scientists understood Mars's current state and informed planning for future exploration missions. But Maya's most significant contribution to planetary science might be her influence on how the scientific community approaches data analysis and the value of diverse perspectives in research. Maya taught us that expertise can sometimes be a limitation, Dr. Torres reflects. Professional scientists develop sophisticated analytical frameworks, but those frameworks can create blind spots that prevent us from seeing unexpected patterns. Maya's lack of formal training allowed her to approach Mars data without preconceptions, and that fresh perspective led to genuine breakthrough discoveries. NASA and other research institutions began implementing Fresh Eyes programs that deliberately involved non-experts in data analysis to identify patterns that automated systems and experienced researchers might miss. Amateur astronomers, citizen scientists, and even students were invited to examine planetary data and propose interpretations without the theoretical constraints that sometimes limited professional analysis. These initiatives led to additional discoveries across multiple space missions, vindicating Maya's demonstration that important scientific insights can emerge from unexpected sources when people approach data with curiosity and systematic thinking. Maya's high school years also brought personal growth beyond scientific achievement. She developed leadership skills through mentoring younger students interested in space science, learned to communicate complex concepts to general audiences, and maintained strong academic performance across all subjects while pursuing her specialized research interests. Her approach to balancing multiple responsibilities impressed educators and mentors, who recognized that Maya's success stemmed not just from intellectual ability, but from discipline, time management, and genuine passion for learning across diverse subjects. Maya showed us that exceptional achievement in one area doesn't require sacrificing well-rounded development, observes Mrs. Anderson, Maya's high school counselor. She maintained strong performance in literature, history, and arts, while pursuing cutting-edge planetary science. Her success came from genuine curiosity about the world rather than narrow specialization. Maya's college application process attracted attention from universities worldwide that competed to recruit someone whose contributions to planetary science had already exceeded what most doctoral students achieve. Her acceptance letters included offers from MIT, Stanford, Caltech, and other prestigious institutions recognized for space science and planetary exploration programs. Her decision to attend MIT was based on the institution's combination of rigorous science programs, collaborative research opportunities, and support systems for students managing professional recognition alongside academic responsibilities. MIT's experience supporting exceptionally talented students provided an environment where Maya's achievements would be celebrated without defining her entire identity. I wanted to go somewhere that I could be challenged academically while also being treated like a regular student, Maya explains. MIT has lots of people who've done impressive things, so being known for Mars discovery wouldn't make me uniquely special. I could just be another student learning from amazing professors and classmates. Maya's freshman year at MIT brought new challenges and opportunities. College-level science courses required mastering theoretical frameworks and mathematical techniques that would enable her to understand planetary processes at deeper levels than her self-taught knowledge provided. The academic rigor was significant even for someone whose research had already contributed to professional literature. But Maya also found intellectual community and collaborative opportunities that hadn't been available in high school. She worked with professors whose research interests aligned with her own, collaborated with graduate students pursuing advanced planetary science studies, and participated in ongoing Mars missions that built on her initial discoveries. Dr. James Wilson, Maya's faculty advisor in planetary science, describes her impact on MIT's research environment. Maya brings both genuine expertise from her own discoveries and fresh perspective from approaching planetary science through unconventional pathways. She asks questions that challenge our assumptions and proposes approaches that wouldn't occur to students who learn planetary science through traditional curricula. Maya's sophomore year brought another major discovery, this time identifying potential seasonal patterns in Mars' atmospheric chemistry that suggested possible biological activity. The finding was preliminary and controversial, but it demonstrated that Maya's ability to identify significant patterns in complex data extended beyond her initial water discovery. The new finding attracted even more attention than her original discovery because it raised questions about whether Mars might currently host microbial life rather than just having been habitable in the distant past. Professional scientists approached the claim with appropriate skepticism, but Maya's track record gave her interpretations credibility that would have been denied to researchers without her proven discovery history. Maya had earned the right to propose controversial interpretations, explains Dr. Rodriguez, who collaborated on the atmospheric chemistry research. Her previous success demonstrated that her analytical abilities were genuine, so when she suggested we look at atmospheric data differently, we took it seriously even though the implications were extraordinary. The verification process for Maya's atmospheric chemistry findings took longer than her water discovery, with research teams worldwide examining the data and proposing alternative explanations for the patterns Maya had identified. The scientific process of rigorous evaluation and peer review proceeded exactly as it should for claims that would revolutionize our understanding of life beyond Earth. By her junior year, Maya had become a leading figure in a new generation of planetary scientists who combined traditional expertise with innovative analytical approaches that challenged conventional thinking. Her work influenced how NASA planned future Mars missions, informed designs for life detection instruments, and shaped theoretical frameworks for understanding planetary habitability. But Maya's influence extended beyond technical contributions to include broader impacts on how society thought about science education, youth potential, and the value of diverse perspectives in research. Maya became a role model for young people who wanted to contribute to science, but didn't fit traditional pathways, observes Dr. Chen, who had become Maya's long-term mentor and collaborator. She showed that you don't need to wait until you have credentials to make meaningful contributions. Genuine curiosity and systematic thinking can lead to important discoveries at any age. Educational programs began using Maya's story to inspire students and demonstrate that scientific discovery isn't limited to professional researchers with advanced degrees. Science classes incorporated citizen science projects that allowed students to analyze real planetary data, following the model that Maya had pioneered through her independent Mars image analysis. These initiatives led to additional discoveries by amateur researchers of all ages, validating Maya's demonstration that scientific progress benefits from broad participation and diverse perspectives beyond traditional professional boundaries. Maya's senior year at MIT focused on her undergraduate thesis, a comprehensive analysis of Mars water distribution and its implications for future human exploration and potential biological activity. The work synthesized her years of research into a coherent framework that would guide planetary science for years to come. The thesis received highest honors and was immediately published as a book that became required reading for graduate programs in planetary science. Maya's synthesis of current Mars knowledge with her own discoveries created a definitive reference that influenced how scientists approached questions about Mars habitability and exploration strategies. Today, at 22 years old, Dr. Maya Patel, having completed an accelerated doctoral program, leads a research team at NASA's Jet Propulsion Laboratory, focused on analyzing data from current Mars missions and planning future exploration strategies. Her position makes her one of the youngest senior scientists in NASA's history, and recognizes her sustained contributions to planetary science over nearly a decade. But Maya's greatest legacy might be demonstrating that breakthrough scientific discoveries can emerge from anyone who approaches data with curiosity, systematic thinking, and willingness to question established interpretations. Her journey from insomnia-driven hobbyist to leading planetary scientist proves that expertise isn't the only path to meaningful contribution. Sometimes fresh eyes and different perspectives lead to insights that transform entire fields of study. Maya showed us that science advances through diverse approaches and perspectives. Dr. Wilson reflects, professional expertise is valuable, but so is the kind of fresh thinking that someone without conventional training can bring. Maya's discoveries demonstrated that we need both experienced scientists and curious newcomers working together to make progress on difficult problems. Maya's influence continues expanding as her research team makes additional discoveries about Mars, and as her example inspires new generations of young people to pursue scientific interests without waiting for permission from traditional gatekeepers. Her story has become a case study in scientific innovation, citizen science, and the importance of making research data accessible to broader audiences who might see patterns that professionals miss. The 13-year-old who couldn't sleep and spent her nights analyzing Mars images became a woman whose discoveries reshaped humanity's understanding of our neighboring planet and proved that sometimes the most important scientific breakthroughs come from those who see data with completely fresh eyes. Maya Patel's legacy extends far beyond specific discoveries about Mars' water or atmospheric chemistry to include fundamental insights about scientific progress, the value of diverse perspectives, and the importance of maintaining curiosity and systematic thinking regardless of formal credentials or professional status. Her journey reminds us that breakthrough discoveries often emerge from unexpected sources, that expertise can sometimes create blind spots that prevent important insights, and that making research data accessible to broad audiences creates opportunities for progress that wouldn't be possible through professional scientists alone. The girl who discovered what NASA missed proved that sometimes the most important scientific advances come not from having more expertise, but from seeing what everyone else stopped noticing, and having the courage to trust your observations even when they challenge established understanding.